Now we're going to talk about the indefinite integral of f of x. In other words, we're going to find an antiderivative of f of x. It's the same thing, indefinite integral. When they say indefinite, they just mean that the limits are not specified as the interval that you're integrating over. So it's just notation that reminds us it came from a definite integral, but all we're calling for is an antiderivative. So, for example, the antiderivative for k, a constant, would be kx plus any constant c. They write this c with a capital letter, standing for any constant. And to verify this, all we have to do is check it. Let's just differentiate kx plus c and see what we get. Well, the derivative of the constant is 0. So it's just the derivative of kx is k, and that's the original integrand. They call the function in here the integrand. And if it verifies out, that's it. Another example, the indefinite integral of x, in other words, the antiderivative for x, is just going to be x squared over 2 plus a constant. Why is that? Well, let's check it. If you differentiate x squared over 2 plus c, the c differentiates to 0, and the x squared over 2 derivative, of course, we've done, is 1/2 factored out of the x squared derivative, which is 1/2 factored out times 2x, which is x. So it checks out to be the same as the integrand, so it is the antiderivative. In general, x to the n, well, it's going to be x to the n plus 1 divided by n plus 1. So you can think of that as x to the n plus 1 divided by the new exponent. As long as n is not negative 1, and we'll discuss what happens in that case next. So you do the check. Here's your check. Let's differentiate x to the n plus 1 divided by n plus 1. Of course, the constant is differentiated out to 0. So you're just differentiating this part. And so we factor out the 1 over n plus 1. And we differentiate the x to the n plus 1, this part right here. And so the n plus 1 comes down in the front. Decrease the exponent by 1. Decreasing the exponent by 1 right here. And the n plus 1's cancel out. And x to the n plus 1 minus 1 is just x to the n. So it verifies out. So there's your procedure. Now when n does equal negative 1, then you have this expression, either x to the negative 1 in there, or it's 1 over x, same thing. So we already know that the derivative of log x is 1 over x. But that's only good for x greater than 0, because the log is only defined for x greater than 0. But this 1 over x function in here, that could be x less than 0. So what are we going to do with that? So we go to our next page, and we see that if we just handle log of the absolute value of x, its graph looks like this. And that matches up perfectly because its slopes, for example here, that's a very shallow negative, so that's a very small negative number. And then here, it's a little bit bigger negative. Right here, a little bit bigger negative. Here, it's a bigger negative. Coming down, it's going to infinity. These things go like this, like that. So these would just go down here, and then on this side, you got a positive slope. Over here, you have a real big positive slope corresponding to this point. Here you have a positive 1 slope. Here you have shallow but positive, real shallow, real low but positive. So this does the trick. Log absolute value of x solves all our problems for that integral. So the final answer to that is the antiderivative for 1 over x dx is log, natural log, of absolute value of x plus the constant. Now we go on to the next page to get some other special ones. The integral of e to the x, just the antiderivative of e to the x, is e to the x, of course. Check that. Take the derivative of e to the x plus a constant. Constant differentiates to 0, and you get e to the x. Integral of cosine is sine, because if you differentiate sine, you indeed get back to cosine. Integral of sine x is negative cosine x, because if you differentiate negative cosine x, you indeed get back to sine x. And here's one, 1 over cosine squared x, which is also could be written as secant squared x. Well, the antiderivative for that is tangent x plus a constant, because if you differentiate that, the derivative of tangent is 1 over cosine x, cosine squared x. So it works out.